What's up, you guys? Hope you guys are still doing well. That was so, that was so energetic, but yeah, what's up, guys? I hope you guys are doing well. This is still your OG GTA, right here with my girls Wendy and Sugi. Did I hold this one right? Happy birthday, belated happy birthday, guys! And you were like, "Sir, why do you have to show up or show out your red velvet uh, energy right now?" Well, I think this one right here, this entire lesson, will be much better to be discussed in line with a birthday cake, And this one is an album by Red Velvet, an underrated one, I think. You may listen to it. I would like to say thanks to my 8H officers and some of the students who gave this to me during the week of my birthday last year. Anyway, so what we're going to talk about today are theorems involving arcs, central angles, and inscribed angles. And I'm saying this now. We're gonna try our best to discuss this in different ways, different interpretation, different techniques. Like again, we're gonna use a birthday cake. We even use a pizza as an example for you to better understand this concept. Well, you know what? Let's just jump right into it. Yeah.
Arcs, central angles, and inscribed angles, and the theorems related to them. So the target that we have here is to prove the theorems. And just to give a hindsight here, or like an idea, we're not going to prove them by two-column proof much, but we're going to show an example, how it looks like. And we're going to try to explain it in different ways so that you'll be able to imagine it better. To continue with these theorems, so the first one is not necessarily a theorem, but a description of congruent arcs. And you already see on the screen what it means. And do not overthink it. The meaning of congruent arcs is that they have equal measures. DA and AB, DA, AB are congruent arcs because their measurements are 40 degrees. And as you can notice on the screen here, again, we're emphasizing that if you use the congruent symbol, you don't include the letter M. But if you use the letter M, you use the equal sign. There's a difference between that. Okay? So the meaning of the symbol right here, the arrowheads, is that it works both ways. That's why you have case 1 and case 2. Because again, it works both ways. So it could be that, again, DA is equal to the measurement of DA, or that arc DA is equal to the measurement of arc AB, or the other way around. It could be congruent. Meaning, if they're congruent, their measurements are equal. If their measurements are equal, then they are congruent. That's what this slide means. To continue, congruent arcs. The theorem now states that if in the same circle or in congruent circles, two minor arcs are congruent if their central angles are congruent. To explain this better, it's the relationship that we have been establishing about circles for a while now. Always remember that this angle right here formed in DPA here, it's a central angle. Therefore, therefore, it is the same measurement as DA. So this will be 40 degrees also. APB is the angle formed here, which is 40 degrees. It's a central angle, hence AB is also 40 degrees. So this is a visual example with values. But without them, if it states that we have here the arc DA and arc AB are congruent, if the arcs are congruent, minor arcs are congruent, therefore their central angles are also congruent. As easy as that. That's why you have the visual representation on the left with values. To continue, now we have one of our theorems in line with congruent arcs. It says here that in the same circle or in congruent circles, two minor arcs are congruent if their chords are congruent. So for example here, you're seeing AB and CD. Now, I know that some of you guys have forgotten about this maybe. If you see a symbol like this, it's called a tick mark. This is called a tick mark or marks. We use them to show congruent sides, or in this case, congruent segments. So if you have one tick mark, that means that those two segments with one tick mark are congruent. If you have two tick marks, then that means that two of those sides are congruent. Okay. In this case, you have AB arc side sorry, segment AB and segment CD that are congruent. Hence, the minor arcs that they formed, you have AC and CD. They will also be congruent. So that's what the first theorem states. Now let's go with central angles. Again, we have established already how what central angles are and their relationship with their minor arcs. Always remember, central angle is an angle whose vertex is at the center of a circle and whose sides are the radii of the circle or the radius. So basically, PB is a radius, PA is a radius, same with PC. That's why radii, because it's in plural form. To continue, intercepted arc. So this will be the focus of the theorems for today. Intercepted arcs. A portion of the circle intersected by two lines or parts of a line forming angles. So since our in this image kasi it already mentions the next one that we're gonna discuss, which is inscribed angles, but we're not gonna go with that one yet. We're gonna go with central angles muna. So our central angle, let's for example, we have BPA. I'll write it down here. We have central angle BPA. So what is its intercepted arc? So the intercepted arc of this one, I'll just put INT please for intercepted. Intercepted arc is basically this one, AB. You may imagine like a pizza. If you cut a pizza, right, you have your angle as the sides of the pizza, the slice, the sides of it, and the crust is going to be its intercepted arc. That's how pizzas work, right? It's impossible for you to cut a pizza and then the crust will be on the other side. It's not the crust of the same pizza. Remember that. So in the intercepted arc here is basically arc AB. And then again, if you want to check out another one, let's say we have angle BPC, for example. Angle BPC. Its intercepted arc will be different. If you cannot see it, BPC, its intercepted arc is from B to C. Therefore, that's their relationship. Again, so you might imagine it in different ways. Actually, some of my students also found this technique wherein if you look at the angle, you will base off your answer for their intercepted arc with the last the first and last letter. So B, C. Here is BA or AB. That's how it works. Okay. Always remember, guys, AB and BA are the same. Okay. Sequence doesn't matter in naming parts unless it's angles or semicircles and major arcs. Okay. I am verifying myself for that. Now, it's a simple relationship. It already says there that AB is 75 degrees. Why? Why is AB or arc AB also 75? Because again, central angle and its intercepted arc are congruent. So probably I've been spoiling this one since the beginning. I'm so sorry. Everything is a cloud right now. But anyway, so again, since APB is 75 degrees, the arc it intercepts is also 75 degrees. Okay? Again, angle APB is 75 degrees. Therefore, its intercepted arc. Is this the correct spelling for therefore? I forgot, man. I'm so sorry. I'm not an English major for a reason. But therefore, arc AB is 75 degrees also. Remember this one. Central angle, intercepted arc equal. Because it's going to be different for the other one. Let's continue. So, this is the thing. Even though we're discussing central angle and in their intercepted arc, you have to remember the basics. What's the basics? Look at the diameter. I'm saying this now in advance. You have the diameter, right? AC. So what does that establish if you have AC? Now, I'm going to teach you a technique here. Do not mind the examples. Do not mind them. Look at this image, find a diameter. So you have AC, right? That's your diameter. So if AB or angle APB is 40 degrees, what will be the measurement of this angle, right? Basic 180 minus 40. The answer there will be, no, I cannot write for some weird reason, 140 degrees. So is that magic? Na 180 degrees minus 40 degrees, 140 degrees. Same case with the one below. We already have 40 and 78. So 40 plus 78 muna, guys. So 40 plus 78, the answer there will be 118, right? Now that you have that, subtract it from 180. Why? Semicircle. What are we looking for? This angle naman, DPE. So 180 minus 118, you will get 62 degrees. Okay? And now, the image is complete. And remember, based off of the first theorems that we have discussed, the measurement of the central angle is the same for their arcs. So, I'll use a different color for the arcs. This is 40 degrees for AB, 40 degrees for AD or DA, 62 degrees for DE, um, BC is 140. We know that EPC is 78. Yeah. Again, central angle and intercepted arcs are congruent. Oh, it's complete. You can answer it now. CPB is 140 degrees. Walang letter M, that's why we can put 140 degrees. EPC, that's 78 degrees. DPE, that's 62 degrees. EA, ayan guys. Arc addition postulate tayo ulit. ED is 62. DA is 40. So, by arc addition postulate, 62 degrees plus 42 degrees. That's gonna give you, I'm gonna show it here, 62 degrees plus 40 degrees. Why am I using yellow? This is gonna give us 102 degrees. Next, arc ABC, that's a semicircle, 180 degrees. BCD, 140 plus 62 plus 78. So that's gonna give us what? 280 degrees. That's it. As quick as that. All you have to do is to remember again the relationship of central angles with its intercepted arcs. And the technique is again, find a diameter so that you have a semicircle. You can finish it that quick. Let's go with next one. Now is the time for you to remember what I've been saying. Central angles and intercepted arcs. Their intercepted arcs are congruent, but it's going to be different for inscribed angles. So an inscribed angle is basically, from the name itself, it's an angle that is still inside a circle, but but the vertex is on the circle now. It's not on the center, on the circle. That's going to be the difference. And instead of it having sides that are radius or radii, it's now chords of the circle. And again, just like the previous example, there will be intercepted arcs. So for example here, you have this kind of figure where you have two overlapping triangles. It can help us see a lot of inscribed angles. So to not be confused here, the technique, guys, one figure at a time. So you have here, for example, EHB. That's your first angle. So just continue with that part muna. After EHB, pwede ka mag HBE. Look at the technique I'm doing. Focus on one first. Oh, mali na ang letter. HBE. Sorry, guys. Sorry. Tao lang. HBE. Last one is going to be BEH. Be. Sa mga walang be dyan. Be. So we're done with the first triangle. Let's go with the other one. So we can have AFD. You have AFD. I'll use a different color for this one. Angle AFD. Next, let's have FAD. We have FAD or DAF. Either will do. And let's have what else? AFD. Okay. You can have FDA. FDA. And what do they intercept? Again, just like earlier, we just use technique or end the letters only. Ayan. So, madali na yan. For EHB, ang intercepted arc na ito, si EB. For HBE, it's HE. For B, it's BH or HB kasi na-hybrid kasi mga B nyo. AFD, AD, that's the arc. For FAD, it's FD. Then for FDA, it's FA. Again, these are the intercepted arcs, but remember again, they're not congruent for inscribed angles. It's going to be different. So let's continue. So for example, here CAB, right? It intercepts CB. Now here DGF, or this angle right here, it intercepts DEF. And then GJI, it intercepts GHI. Kapag one letter lang ginamit, guys, that's the vertex, which is J. So that's how it works. Let's continue. Now, this is the theorem that I've been mentioning. The measure of an inscribed angle is equal to 1/2 of the measure of its intercepted arc. So, for example, what you're seeing here, inscribed is angle CAB in circle P. The measurement of angle A is 1/2 the measurement of arc CB. Now, there will be a proof shown after this, but we can try to figure it out here with this slide first. So, in order to prove this, we have to remember the different things that are related to, geometry. And the thing here that I can suggest to you guys is you have to widen up your imagination so better understand this. The first thing that I would like to mention is that the thing here to explain this better is you have to really illustrate it. So from C to P, I will draw a line segment CP. Okay, so that's the first thing, or draw PC. So what the first thing that I did here, I'll write it here. Draw PC, right? Or segment CP. Draw PC. Okay. Now, after drawing this segment right here, what do you think is PC or segment PC in line with the other parts of this given? PC is a radius. Oh, radius. Why? Center, point on the circle. Okay? So, if it's a radius, this is an informal proof, by the way. I'll show you the complete one after. I just want you to see it firsthand so that you can imagine it better. So, again, segment PC is a radius. So, if segment PC is a radius, is it true that PC is going to be congruent to AP? Yes, that's because they're both radius or radii at this point, right? So I'll put tick marks here, one here, one here. Why? So that you will remember it later. Now, look at the image we have here. Were we able to form something? Yes, we are able to form something here. We were able to. And that is a triangle. What kind of triangle is this? Isosceles. So we have triangle APC is an isosceles triangle. What do you mean by isosceles triangle? Basically, two sides are congruent. That's how it works. Now, since APC is an isosceles triangle, that means the angles related to those two congruent sides will also be congruent. So meaning, we can say that angle CAP is congruent to what angle? Angle ACP. Now, in this case, we will proceed with another kind of angle that we're going to see here on the outside. Okay, now you might be wondering, what is that angle for? And what is that angle at all? You might not remember your grade 8 mathematics, which is understandable, but we have to recall it a little bit here. So for number 6, you have angle CPB. The measurement of that is equal to the measurement of angle CAP plus the measurement of angle ACP. You're like, sir, why? What is CPB in line with the image? That angle. Is it inside the triangle? Is this inside the triangle? No, it's outside. And if you remember back in, again, grade 8, we call this as an exterior angle. And number 6 here is an application of the exterior angle theorem, where the exterior angle is equal to the measurements when you sum, the measurement of the exterior angle is equal to the sum of the measurements of its two remote interior angles. So this is the exterior angle theorem. In that case, when you proceed here, now how will we relate this with the concepts of CPB is central angle, right? Do you agree with that? It's central angle. And then you have CAP, AP, ACP, they're both congruent. So what do you think should be the next step for us to again prove that angle A or CAB is one half of arc CB? So we'll now try to substitute here. So is CPB equal to the measurement of arc CB? Yes, that's a theorem we discussed earlier. CPB again is congruent to CB. Next, CAP is our angle A. How do we prove that it's one half? That's the challenge now. So, what do we do next? CAP and ACP. What do you think should we do here? We can use one letter, which will be used for the proof later on. You will look at number 5 again. Look at number 5. CAP and ACP are congruent. So, if I were you, I'll just simply say the measurement of CAP plus the measurement of CAP. What happened here? Look at number 5. Since they are congruent, what I did is I substituted. So we're going to have measurement of CB or arc CB equal to 2 measurements of CAP. And divide both sides by 2. Hence, you'll get 1 half of arc CB. Ooh, di ko pa rin get, sir. Okay lang yan. Pares lang tayo. Joke. So, in the proof, as you can see here, again, that was an informal proof to somewhat lead you to this one. We draw CP because, again, 2 points determine a line. That's your radius. CPB is a central angle. That's true. And then, again, CPB, this one, intercepts arc BC or CB. Next, AP and CP are congruent. Why? Because, again, radius. Guys, radius. Radii. CPA is an isosceles triangle. Radius or radii, again, have the same measurement. Next, angle C is congruent to angle A. That's the isosceles triangle theorem. The relationship, again, if there are two congruent sides, then the angles opposite to them are also going to be congruent. And then, measurement of CPB, this angle right here, is equal to the sum of the angle in C and A. That's by exterior angle theorem. And again, we substituted based on this. Since C and A are of equal measurements, we can substitute that. So if you add 2 measurements of angle A, that's going to be your answer here. So to simplify this, you can multiply both sides by 2 or divide, depends on you. it will lead you to number 11. And then again, how did CPB become CB? How did an angle become an arc in this kind of solution? Basically, again, remember, CPB is central angle and it's equal to the measurement of its intercepted arc. Hence, the proof for the inscribed angle theorem. But we are not expecting you to remember how to prove this. We just want you to understand how it all happened. And basically, all we need you to remember is that the inscribed angle is equal to one half of its intercepted arc. So let's just jump right into it, right? Now we're here. Corollary 1. So two inscribed angles of a circle intercept the same arc or congruent arcs, then the angles are congruent. I know the answers are on the right side already, but for some that are having a hard time with this one, let's start with ADB. Start with ADB. Okay? So ADB is an inscribed angle. Its intercepted arc is none other than AB. Do you guys agree with that? Now, what does corollary 1 mean? I'll use a different color for AEB. So AEB. Therefore, as you can notice, they still share the same arc. That's why they are congruent, because it's basically the same intercepted arc. And then another one, there's another one here, guys. You can also have AFB, same arc still. Because of that, again, not only are, it's pretty obvious, AB is the common denominator here, arc AB, since they share the same intercepted arc. Okay? That means all those angles are congruent. That's corollary 1. Next, corollary 2. It's not complicated, let's not make this complicated. If a quadrilateral, by quadrilateral, four-sided figure, four sides, inscribed, meaning again, inside a circle, then its opposite angles are supplementary. By opposite, A is opposite to C, D is opposite to B. And by supplementary, guys, please do not forget, supplementary means it's the measurement of two angles, and if you add them, it's equal to 180 degrees. Now, there's a lot of questions that's going to be dealt with in this one. Like, sir, it says opposite, right? But will there be cases wherein consecutive angles will be supplementary? Of course, yes, but not all the time. So, what example am I talking about here? If I draw a square inside a circle, opposite angles are still supplementary, but also consecutives. But again, this is not true all the time. That's why the word is quadrilateral. There's more to life than squares and rectangles. There are kites, rhombus, trapezoids, and so on. Okay? But again, that's a counterexample lang, or a trivia, or whatever you want to call it. So let's proceed with corollary 3. Now, if an inscribed angle intercepts a semicircle, then the angle is a right angle. You know what? This one doesn't have to be complicated though. You have here angle ACB, right? I'm highlighting it. So the angle ACB right here, what makes it a right angle? This is the explanation that I'll give. It's a student explanation also. Look at it. It's connected by what? That's the diameter. So you may imagine it like this. If again, if the inscribed angle share the same endpoints as the diameter, it intercepts a semicircle. And what's the measurement of a semicircle? Semicircle is 180, right? And what's the formula that we established earlier? Inscribed angle is equal to one half its intercepted arc. So if ACB intercepts a semicircle, so what is one half of 180? It's equal to 90. That's it. Corollary tree doesn't have to be complicated. It's just the application of the formula. Okay? So again, a trivia or a concept or an idea is that you base it on the endpoints. If again your inscribed angle shares the same endpoints as the diameter, you can automatically say it's a right angle. Again, that's just a student explanation that I receive from my kids. That's how they see it, and that's how I see it too. But again, I'm just wording it out, giving you guys heads up that this is the textbook's explanation, and what I gave is student explanation. Now let's go with corollary 4. This one, I think you can look at your clocks or watches if they're like the regular ones, not the digital one. So basically, if you have parallel segments, I want you to take a good look at this. If there are arrowheads on top of the segments instead of the tick mark, it's different. Okay? Ayan o, may arrowheads ka dito. Ang meaning niyan guys is parallel. Okay? What makes this congruent? Yung AC tsaka si BD. I was telling my students here to look at the clocks that they have, especially if they're not digital, right? Imagine your clock, right? It's not. This is not gonna be perfect, but if you look at your clocks, I have 12, 6 here, this is 3, this is 9, right? You have 1, 2, 4, 5, 7, 8, 10, 11. So for you to imagine this, try to draw two congruent segments from 11 to 7 and 1 to 5. Parallel segments. That's going to be parallel 11 to 7, 1 to 5. Now count the number of markings from 11 to 1 or 5 to 7 or 7 to 5. If you counted the marking including 7 and 5, that will be 10 for both of them. If you don't include them, it's going to be 8. If I'm not mistaken, they're congruent. So if you have a clock on your classroom, this will be kind of a cheat code if you understand the lesson in circles. Again, that is one of the best applications of circles in real life. Application, I mean. My God, my grammar is not grammaring anymore. But I hope you understand that. Now let's have an example. Let's have a quadrilateral and this one right here. And we will use this quadrilateral in order for us to answer everything. So I'm going to help you out with this one. The technique again is, guys, do not mind the questions. Let's try to complete it first. Now, it's kind of cheating for me because I can erase the coloring, so you have to be careful with this one. Because I suggested my kids to like color their outputs in terms of lining to guide themselves. Your choice. So I'll start with this one. I see DC, sorry, angle DBC, right, and angle DEC share the same intercepted arc. So if DEC is 30 degrees, therefore DBC should also be 30 degrees. As simple as that. So I'll put 30 degrees here. Okay. Next. What else? Okay. Fresh from earlier. We have dab. So dab on them haters, right? Dab. And again, as you can notice, there is a diameter dB. Like I said, diameter is your cheat code here. So since it's a diameter, that's an inscribed angle, guys. So therefore, this this is the semicircle it intercepts. Therefore, dab is going to be equal to 90 degrees. Why is dab 90 degrees? It intercepts the semicircle. Okay, this is 90 degrees. What's next? Okay, next. We have to do something with this 80 degrees here. If you look at ABD, it intercepts AD. And again, remember relationship of the intercepted arc and the inscribed angle is that the inscribed angle is equal to one half. Again, inscribed angle is equal to one half of its intercepted arc. So 80 divided by 2, you will get here as 40 degrees. Now, I want to deal with something here first. We established earlier that inscribed angle is equal to one half its intercepted arc. So just like earlier, you have to really derive the formula, or no, not necessarily anymore to be honest, but if you just have to remember it. So if an inscribed angle is equal to one half its intercepted arc, if you multiply this both sides by 2, right? This means that twice the measure, wait, the PDF is saving, right? Twice the measure of the inscribed angle is equal to what? 1 half times 2, that's going to be equal to 1. It's going to be equal to the intercepted arc. Get it? So if an inscribed angle is equal to 1 half the intercepted arc, therefore, the intercepted arc is equal to 2 inscribed angles. If you're like, sir, what are you saying? Like, for example, DBC, right? The angle is 30 degrees. Therefore, DC is equal to 60 degrees. That's how it works. I mean, imagine it like that. Now, this helps us actually in completing this thing. Like, for example, earlier I've been establishing the importance of knowing semicircles and the diameter. So, look at this image right here, right? This is a diameter. Therefore, it states that this should be what? This should be what? A semicircle. If DA is already 80 degrees, what should be the measurement of AB? Well, 180 minus 80, you'll get 100. So this should be 100 degrees. Again, I have highlighted earlier the diameter dB or BD, and then from there, we have 100 degrees. The importance of this one, again, is for you guys to understand that this will help us out a lot in identifying the other measurements, if necessary. Okay? What else do we need to find here? Okay, this one. Look at this one. ADB. What is that? It's a triangle. And always remember, guys, always remember, if you have a triangle, right? The sum of its interior angles will always be equal to interior angles. There are only like three angles for interior of a triangle, right? It's equal to 180 degrees all the time. So 90 plus 40, that will give you what? 130. So 180 minus 130, you will get here 50 degrees. Now, now we have 50 degrees, 90 degrees, 40 degrees, and 30 degrees. And it's true, right? If you notice, ADB intercepts AB. 100 divided by 2, 50. Correct. What else? Okay, meron pa. Dami pa yan. DCB, that intercepts a semicircle again. Okay? Because again, it connects to the diameter. Therefore, this one right here should be a right angle also. This one is equal to 90 degrees. Since that is 90 degrees, we can state that BDC, 90 plus 30, that's going to give us what? 120. 160 minus 120, we'll get here 60 degrees. Because may triangle tayo ulit, guys. Kung hindi nyo kita. 90 plus 30, 120. 180 minus 120, get 60. I think that's more than enough. Is it? Yeah, let's see. So the measurement of DAB, let's see. Angle DAB is 90. ABD, 40. Ganun yan, guys. The middle letter is the vertex. So that's the angle. DBC is 30 degrees. DCB is 90. What's next? BDC, that's 60. ADB, that's 50. How about ADC? I want to see this one though. ADC. So you can notice, it's the angle formed here. So 50 plus 60 siya. So the answer is 110. Same case for ABC. ABC. So it's this angle right here. 40 plus 30, the answer will be 70. So that's it. And we're gonna have our last example. Finally, the end of the yapping. Here we have here again. Let's try not to think of the questions or things we're looking for. Let's start here. RT is a diameter. Diameter na si RT, mentioned na. Diameter daw si RT. So if RT is a diameter, and you already have 70 degrees here, 180 minus 70, the answer is 110. So 110 na si SR. Next. Si RV tsaka si ST. I want you to take a good look at this. Oh, RV, one of my favorite initials. Red Velvet, guys. ST plus RV. And ayan, guys, oh, parallel. Just like the clock, right? So if ST is 70 degrees, RV will also be 70 degrees. We established that earlier in the corollaries. Next, so kung si RV 70, ano measurement ni TV? 110 din. We're gonna prove this in the future why SR and TV results to two congruent arcs then dito. Okay, ano pa meron tayo? Ayan, look at this one. SPT. What's that? That's a central angle. It intercepts ST. So pag central angle, guys, don't forget, equal. So this is 70 degrees. I'll remove the sign. 70 degrees lang. Next, SPR, central angle then. Therefore, this one is also 110 degrees. Now, RTV, is that a central angle? Nah, it's not. It's an inscribed. So 70 divided by 2, you will get 35 degrees here. Next, what else? What else can we have? Yan, SRT then, guys. SRT. SRT. That's another inscribed angle. It intercepts ST. 70 divided by 2, you will get 35. Oh, look what do we have here. Triangle again. So 110 plus 35 degrees, 145. 180 minus 145, 35 degrees then. Wow. We have an isosceles triangle here. So the nuggets. Again, remember, guys. Triangle equal to 180 degrees. Interior angles. Remember, central angles congruent or equal to intercepted arc. Kapag inscribed lang siya, guys, equal to 1/2 of intercepted arc. Always remember, semicircle, also 180 degrees. I'm not kidding. These 4 things will help you fill out the entire triangle. Oh, sorry, circle. Ano ba meron tayo dito, guys? RST. And RST, guys. You see it? RST. It's connected to the diameter. Hence, RST must be equal to 90 degrees. So, kung 90 degrees si RST, and there's already 35 degrees here, what's 90 minus 35 degrees? It's gonna give us what? 55 degrees. And look what we have here. Another triangle. So, 55 plus 70. And, you know what? Look at this, guys. SP, PT, radius, isosceles triangle ulit yan. So, dapat 55 din to. Is that true? 55 plus 55, 110 plus 70, 180. And another one, look at this. 55 and 35, 90 degrees. Why? Because of what? STV. It intercepts SRV. 110 plus 70, 180 divided by 2, 90. Wow. Joke lang. Antok na ako, guys. Antok na rin ko. Pero yung point ko is, you can apply all of these things, all of them, to really fill this thing out. Let's see if we're complete. Okay, TPS. Si TPS ay TPS, that's 70. Okay, SRT, SRT 35, SPR 110, RTV 35, STR 55, TSP 55, RST, and how am I loading? 55 plus 35, get 90. RSP will get 35 ulit. STV, you get 90. And that's it. That ends our lesson with the theorems involving central angles, inscribed angles, and the arcs. What do you have to remember? It's basically these things. This will help you out a lot. If ever, again, I yapped for like 10 hours here, but what I want you to simply remember is central angles is equal to its intercepted arc, and the inscribed angle is equal to one half its intercepted arc. Or in this case, intercepted arc is equal to one half its inscribed, two of its inscribed angles. Now, I blabbered there, but yeah, that's it.
And that ends this video about the theorems about arcs, central angles, and inscribed angles. I hope you guys learned a lot from this one, even though there are some complicated things in the middle or by the end wherein we have proving. It's a necessary thing that we have to do. And you might be thinking, sir, why are we doing proving in mathematics and geometry? Well, blame the philosophers that were alive years ago. Like, uh, let me yap for a second here. Geometry, like most of the people who were involved in geometry back in the old days were actually philosophers. Like, for example, Rene Descartes is a philosopher. He's partially one of those people that you kids are blaming for, you know, geometry, but and algebra altogether. But he's one of the best ones out there because if you understood the concept of the Cartesian plane and the way we now incorporate different images on it. And speaking of that, I'm gonna do something about that one. A late one at that, but I hope it goes well. So we're gonna have an outtake for that, for the Cartesian plane and artwork kind of vibe. We'll do one on that, and at the same time, um, geometry and proving is, I think for me now, I really enjoy it a lot because it became the bridge that showcases not only our skills in drawing, sketching, imagining, but also with our problem solving and critical thinking skills. Like, imagine the example we have here. We started with an inscribed angle only and a circle, of course, and then by drawing a radius, we were able to prove the relationship of the inscribed angle with the circle. I think that's the beauty of it, like by sketching. And that's what we're gonna do a lot, especially in the next video. We're gonna sketch based off of the understandings that we have from triangles, circles, and so on. So yeah, it's going to be a rocky road from here, but don't worry. You got me, I got you. And again, in case you don't see me, good morning, good afternoon, good evening, and good night.